Jovian planets are fascinating objects. Jovian planets. The Jovian planets are Jupiter, Saturn, Uranus, and Neptune. These are all very large objects. Jupiter is what? 318 times the mass of the Earth. Saturn is 95 times the mass of the Earth. Uranus is, what's that, about 14 times the mass of the Earth. Neptune, 17 times the mass of the Earth. These are big objects. And remember, the Earth is the largest of the terrestrial objects. So these are really totally different objects. Our general theory is that right near this, in order for these to form and be such colossally different objects than the terrestrials, well, near the sun, it's hot. To make a planet, you need solid materials, so only rocks and metals are solid, so you build rock-metal planets. Farther from the sun, beyond the orbit of Mars, outside the frost line, you've got the ices, water ice, methane ice, ammonia ice, carbon dioxide ice, and so then you have, I don't know, 3 times, 4 times more material than if you just had rocks and metals. So you build up planetary nuclei out of rocks, metals, ices that are 4 or 5 times the mass of the Earth, maybe more. And then once you get over that threshold, you got to have about 5 times the Earth mass in order to hold on helium and hydrogen. And helium and hydrogen are most of the universe. 98% of the stuff in the solar nebula was hydrogen and helium. It's just, you know, most of the Earth couldn't hang on to it. Its gravity's not strong enough. And then once you can hold on to that, then you can get enormous sorts of things. You start out with this core, 5, 10 times the mass of the Earth, and then you pull in hundreds of Earth's masses worth of hydrogen and helium, and then you've got this huge sort of object. So the first thing we need to know, let's see, so there's a quick sketch. And so these are made of a mixture of both. There is solid material down in there somewhere. There's some liquid material. There's a lot of gaseous material. Whereas, I mean, if you look at the Mercury, Venus, Earth, Mars, they're all mostly rocks and metal. That's what we're talking about. So how do we know this? That's the key question in order to understand the science really well. What evidence leads us to this conclusion? You get a planet like Saturn, and if our calculations are right, then Saturn has a density less than the density of water, which means if you could take the planet Saturn and put it in a bathtub, the planet Saturn would float. It's less dense. It's not true of the other Jovians, but Saturn in particular is mostly gas all the way through. How do we know that? How do we know that Saturn's density is so very, very, very low? I mean, all we can see visually is we can see the tops of the clouds, and no light comes from much deeper than the tops of the clouds. Everything we see are the clouds and above. And so we can use spectroscopy, we can use emission and absorption lines to measure the chemical content of Saturn's outer atmosphere. But how do we know there isn't a solid surface? How do we know it isn't rocks and metals just underneath those clouds? The evidence there comes from its mass, which comes from its moons. When you study the moons of Saturn, we use Newton's version of Kepler's third law to then calculate what the mass of Saturn is. Then we can take the volume of Saturn and the mass from the orbits of its moons. If it was rocks and metals in there, it would have a much stronger force of gravity, and so its moons would be orbiting a lot faster. Because the moons of Saturn orbit relatively slowly, that tells us that Saturn's mass is only 95 times the mass of the Earth, which for its diameter tells us that the density of Saturn is less than the density of water, which tells us what's going on in its interior. That's how we know what's going on inside these planets. In bulk, the first calculations we do are we study the orbits of the moons that tell us the mass, then we take the diameter, calculate the density, and then that's how we know that Saturn is mostly gas, whereas Neptune has a substantial solid core in there, and then, you know, it has a mantle of liquid and then there's gaseous materials around it. Fascinating sorts of things. Another interesting fact about the Jovian planets is they rotate fast. They rotate fast. I mean, a day on Jupiter is only about half of what a day on the Earth is, and you got to remember Jupiter is like what, you know, it's a lot bigger than the Earth, and so its velocity of rotation is enormous. The Jovian planets all rotate very, very quickly, much faster than the terrestrial planets, and that's what causes all the clouds on like Jupiter and Saturn and Uranus and Neptune, causes these clouds to line up in these east-west bands where you've got these, you know, these belts and zones, and, you know, and then there's the red spot in there doing its sort of thing like this. And so the clouds this causes clouds to line up. east, west. It's exactly the same effect which drives the jet stream here on the Earth. Okay, there's the jet stream. You know, high altitude brings weather around and it flows from west to east across the country. Well, the reason why it flows in that direction is because of the Earth's rotation. If you were to grab the Earth and stop the Earth from rotating, then things like the jet stream would go away. These big circular patterns are related to the fact that the Earth is rotating. Because Jupiter rotates so amazingly fast, that causes a cloud to climb up. And if you were to grab the Earth and spin it up even faster, then our clouds and these weather patterns and these circulation currents would line up east-west even more. When we start looking at Jupiter and stuff like this, we see basically 3 cloud layers. You know, you can see these belts and zones, different colors. It's really interesting, these things going on there. Because, well, here on Earth, all of our clouds are made of water. The low-altitude clouds are tiny droplets of water suspended in the air. High-altitude clouds are little crystals of ice, solid water, up in the air. But all of our clouds are made of water in one form or another. When you look at the planet like Jupiter, then you find that there are actually 3 substances that make up its clouds. Ammonia, ammonium hydrosulfide, and then the deepest in layer is water. So we can actually see in the deepest in layer, you know, water, flecks of water ice create the deepest in layer of clouds. And so when we see these belts and zones, we're seeing different regions. There are some where we've got warm air coming up and then cool air going down. Convection, heat rises, cools, sinks. Well, that's going on with Jupiter right now all the time. And then at the deepest in layer of clouds, the water clouds, well, we can actually we can see lightning and all sorts of interesting effects going on in there. Whereas ammonia and ammonium hydrosulfide, they don't tend to produce lightning because water has a negatively charged oxygen atom on one side and positively charged hydrogens on the other. So it's polar, whereas, you know, ammonia is a nonpolar molecule. All the charges are spread around evenly. And so you get all sorts of fascinating things. You get these storm patterns going on. The great red spot of Jupiter, an amazing colossal storm which has been raging for hundreds of years. Why does it keep going? Well, let's think about why storms on Earth dissipate. You get these big giant hurricanes that form down in the Caribbean Sea, tropical seas. And they're fed. Where does the energy from a storm come from? Well, it's this warm air rising off of the warm water. And so then your hurricane goes and it becomes a huge storm and then it comes over land. And then it's not over this warm water source anymore, and so then it gradually dissipates away. Or another way, it can go from the tropical things up to the North Atlantic or North Pacific, or far from the equator. And again, it doesn't have this source of warm water to drive it, and so it dissipates away. You look at a planet like Jupiter, and, well, there's no land there, so it's not going to dissipate in that way. And it's also confined because it's spinning so fast. It's very much more difficult for storms to move north or south away from equatorial sorts of regions. They're kind of locked into the same sort of region. They're locked into that region, and so they're going to be much more stable. They're not going to move over regions with less or more heat or that sort of thing like this. And then the heat source, which is the interior source of Jupiter, that's going to be a much more steady sort of thing. Jupiter is still giving off more heat energy than it receives from the sun. It's basically heat of its formation. You know, gas, as it contracts, as gravity pulls it together, gets hot. It gives off heat energy. When you pump up a tire, push all that air in there, the tire tends to get hot. That's the effect here. Jupiter's still settling in that sense. 4.5 billion years after it formed, it's still settling, still giving off energy as its gas is gradually compressed more and more. Another great fact about Jupiter in particular is it has this amazingly colossal magnetic field. Jupiter's magnetosphere is the largest structure in the solar system after, you know, the sun and all it puts out. If you could see, you know, you look at Jupiter in the night sky and it looks like a really bright star, but if your eyes could see radio waves, could see that magnetosphere, you would see that Jupiter's magnetic field, even from here on Earth, would look as big as the full moon. It's an absolutely enormous structure. And so then we have to ask a question, well, how do you generate a magnetic field? Well, here, for a terrestrial planet, you know, okay, to generate a planet-sized magnetic field, you need a conducting material, which is liquid, and is convecting and rotating. And so to generate a planet-sized magnetic field, there we go, you need a liquid conductor that is rotating And convecting. Convecting meaning that hot material is rising and cooler material is sinking. You know, kind of a boiling sort of a pattern. And so with the Earth, well, we know what's going on in the core of the Earth. That's liquid iron in the core of the Earth, which is convecting. Hotter amounts are going up, you know, in the outer core of the Earth, and then going back down in, and then it's rotating every 24 hours. That's why the Earth has a strong magnetic field. Venus does not, because it's not rotating very fast. Mars, Mercury, and the Moon don't, probably because they don't have so much liquid inside them. Then you look at something like Jupiter, and Jupiter has this colossal magnetic field. It's like, well, you know Jupiter's not made of mostly iron. There's some iron in there, but not that much, not on a percentage-wise. So how does Jupiter generate this colossally powerful magnetic field? And it tells us, well, it's not iron, but there must be some other liquid, fluid conductor in there. So when we do our calculations, we find that much of the hydrogen inside of Jupiter is under so much pressure that it breaks the individual electrons free of their protons, breaks them free of their nuclei, so that they can move about freely. And so your hydrogen becomes a liquid conductor. So we have the substance called liquid metallic hydrogen, which is deep inside Jupiter there. And that must be what's in there. That's the only thing we can think of which could generate this powerful magnetic field. You need a liquid conductor. Jupiter's mostly hydrogen, so somehow you got to make hydrogen into a conductor, and our calculations say that that should be possible. That if you put it under enough pressure, then electrons break free of individual nuclei, and so that it's a conductor, and then it can generate currents and make powerful magnetic fields. Jovian planets are amazing, amazing things.